In this section, we will deal with a variety of electrophilic addition reactions to alkanes, beginning with the bromination of alkanes. Electrophilic addition of bromine to ethylene results in 1,2-dibromoethane. The reaction mechanism involves two steps and goes through a bromonium ion intermediate. Step 1. One of the bromine atoms initially acts like an electrophile due to the induced polarization of the Br-Br molecule. The pi electrons attack the Br-Br molecule. This results in the breaking of the Br-Br bond, formation of the first CBr bond, and the simultaneous attack of the bromine on the electrophilic carbon, resulting in the cyclic bromonium ion in one step. Br is surrounded by an octet of electrons, and this renders stability to the system. Step 2. Br minus attacks the cyclic bromonium ion from the opposite side in an anti-addition mode and opens the three-membered ring, resulting in the formation of 1,2-dibromoethane. Bromination of alkenes is a highly stereospecific anti-addition reaction. Evidence for the reaction mechanism for the addition of bromine to alkenes. Cyclohexene undergoes anti-addition with bromine to give exclusively trans 1,2-dibromocyclohexane. This is possible only if the reaction goes through a bromonium ion. The bulky cyclic bromonium ion would block any syn addition due to steric crowding. If the reaction were to go through a carbocation intermediate A, a mixture of cis and trans 1,2-dibromocyclohexanes would be formed, since the second bromine can add from either direction. Addition of hypohalous acid to alkenes. Preparation of halohydrins. The reaction of ethylene with bromine in the presence of water results in the formation of bromoethanol, a halohydrin. The reaction mechanism involves two steps. Step 1. The bromonium ion is formed first, as in the case of the addition of pure bromine. The bromonium ion is attacked by water molecule from the opposite side to form a protonated halohydrin. Abstraction of a proton from this by H2O will give bromoethanol. Addition of hypohalous acid to alkenes is a highly stereospecific addition. Evidence for the reaction mechanism for the addition of hypohalous acid to alkenes. When bromine is added to methyl cyclohexene in the presence of water, only one stereoisomer, trans 2-bromo-1-methyl cyclohexanol, is formed. This is possible only if, after the formation of the bromonium ion, water attacks the bromonium ion from the opposite side in an anti-addition mode. In this reaction, water is the nucleophile rather than Br minus, since it is present in greater amount. In the above reaction, note that water attracts the carbon carrying the methyl group. This is due to the fact that this will create a more stable incipient tertiary carbocation than the attack on the other carbon, which would create a less stable incipient secondary carbocation. Preparation of alcohols from alkenes. Hydroboration-oxidation. Hydroboration involves the addition of borane to the double bond in an alkene to give an alkyl borane. Oxidation of the alkyl borane with hydrogen peroxide and sodium hydroxide gives an alcohol. For example, when propene is treated with borane, propyl borane is obtained. This is oxidized using hydrogen peroxide and hydroxide in water to give propyl alcohol. In the above reaction, borane acts like an electrophile. Borane has got only 6 electrons around its nucleus and hence is a Lewis acid and seeks out the pi electrons. Note that in the above reaction, boron, being bulkier than hydrogen, seeks out the less crowded carbon, and hydrogen seeks out the more crowded carbon. Note that the regioselectivity is opposite to that for the addition of hypohalous acids to alkenes. In the above reaction, both boron and hydrogen add to the double bond on the same face of the double bond, resulting in a syn addition product. Reaction mechanism for hydroboration-oxidation of alkenes. The hydroboration-oxidation of methylcyclohexene results in the formation of trans-2-methylcyclohexanol. Step 1. Borane adds in a single step, forming the boron carbon and hydrogen carbon bonds on the same face of the double bond to give alkyl borane. The regiochemistry of addition as above is preferred since in the transition state, any partial positive charge generated on the tertiary carbon would be more stable than if the alternate way of addition takes place. Also note that boron seeks out the less crowded carbon. Step 2. The intermediate alkyl borane is oxidized to a hydroxyl group with hydrogen peroxide and sodium hydroxide in water. The hydroxyl group replaces the boron on the same side, resulting in another syn addition, forming an alcohol. Oxymercuration-reduction of alkenes. Preparation of alcohols. Oxymercuration followed by reduction is an excellent method for the preparation of alcohols from alkenes under mild conditions and without the fear of carbocation rearrangements. Example, when propylene is treated with mercuric acetate in water, it undergoes electrophilic addition and gives an intermediate organomercury compound. Reduction or demercuration of the organomercury compound with sodium borohydride gives the alcohol 2-propanol. Note that the overall reaction follows Markovnikov regiochemistry. Mechanism of oxymercuration-reduction reaction. Methyl cyclohexane, when treated with mercuric acetate in water, followed by reduction with sodium borohydride, gives 1-methyl cyclohexanol as product. Methyl cyclohexane, when reacted with mercuric acetate, undergoes electrophilic addition and gives the mercurinium ion as the intermediate in one step. Water attacks the more substituted carbon and opens the ring to give the organomercury compound. Reduction with sodium borohydride yields 1-methyl cyclohexanol. Reaction of alkenes with peroxy acids. Preparation of epoxides. Ethylene, when treated with peroxy acids, forms ethylene oxide and epoxide. Epoxides are cyclic ethers in which an oxygen atom is part of a 3-membered ring. Reaction mechanism. The hydroxy group of the peroxy acid has a positive charge, making it electrophilic. The reaction takes place through a concerted mechanism in which all the bond breaking and new bond formation are simultaneous. The reaction always results in a syn addition. Cyclohexene, on reaction with metachloroperoxybenzoic acid, gives cyclohexane epoxide. Stereospecific ring opening of epoxides to form trans 1,2-diols. When treated with aqueous acids, epoxy ring opens stereospecifically to give trans 1,2-diols. Example, when cyclohexane epoxide is treated with aqueous acid, it gives trans 1,2-cyclohexane diol. When cyclohexane epoxide is treated with aqueous acid, the acid protonates the oxygen atom of the epoxide. This makes the carbon attached to the oxygen atom more electrophilic, and water attacks the carbon from the side opposite to that of the epoxide ring and opens the epoxide ring. This results in the formation of an hydronium ion. Another water molecule picks up a proton from the hydronium ion to give trans 1,2-cyclohexane diol. Reaction of alkenes with osmium tetroxide. Preparation of cis 1,2-diols. Preparation of cis 1,2-cyclohexane diol from cyclohexene. Cyclohexene, on treatment with osmium tetroxide, forms a cyclic osmate. The reaction occurs by a concerted addition mechanism with syn stereochemistry. The cyclic osmate, upon oxidation with hydrogen peroxide, results in a cis 1,2-diol with the regeneration of osmium tetroxide. Reaction of alkenes with ozone. Formation of carbonyl compounds. Z3-methyl-2-pentene, on reaction with ozone followed by reduction, yield ethanal and 2-butanone. Ozone, being a good electrophile, adds across the double bond to form molozonide. The molozonide immediately and spontaneously rearranges to form ozonide. Note that both the sigma and pi bonds of the alkene have been broken. Reduction of the ozonide with zinc and acetic acid results in the carbonyl compounds ethanal and 2-butanone. From the structures of the carbonyl compounds formed, we will be able to deduce the structure of the original alkene, and hence this reaction is useful for structure elucidation. Catalytic hydrogenation of alkenes. When propane is treated with hydrogen in the presence of metal catalyst like platinum or palladium, the hydrogen molecule adds across the double bond to give propane. Reaction mechanism. The sigma bond between the hydrogen atom breaks on the metal surface and the hydrogen atoms bond with the metal. The pi bond in the alkene also breaks on the metal surface and the carbons bond with the metal. The reaction between them at the metal interface forms alkane. The hydrogenation of 1,2-dimethyl cyclohexene gives only cis 1,2-dimethyl-cyclohexane. This shows that catalytic hydrogenation of a double bond involves stereospecific syn addition.